All right, let's jump right in. We usually think about AI finding that one single perfect answer to a problem. But what if the real world is messier than that? What if it demands more than just one perfect plan? Today, we're going to dig into a really cool paper that explores a new way for AI to discover a whole library of smart solutions, which makes it way more adaptable. This is Policy Manifold Search.
So, take a look at this robot. Using a technique called neuroevolution, which is basically natural selection for an AI's brain, we can get it to master a task like walking. It tweaks millions of tiny settings in its neural network until it finds a single, super efficient way to move. It's really impressive, and for a long time, this has been the gold standard.
But, and this is the big but, what happens when things go wrong? That one perfect solution is actually pretty fragile. If a leg gets damaged or the ground suddenly gets icy, that perfect walk might become totally useless. The robot would just, well, it would fail.
So here's the key takeaway. For an AI to be genuinely tough and useful out in the real world, it needs something researchers call behavioral diversity. It needs a whole collection of different ways to get the job done, different ways to walk or kick or grab. It needs a plan B, a plan C, a plan D. You get the idea.
Okay, but finding that library of solutions, that is incredibly hard. And why is it so hard? Well, because you're searching through a space of almost infinite possibilities.
To really get a grip on this, we have to talk about the policy parameter space. Now, that sounds super technical, I know, but think of it like the giant control panel for the AI's brain. Every single knob and switch is a setting, a weight, or a bias. A modern neural network can have millions of these. All the possible combinations create this astronomically huge, high-dimensional space.
And this picture just perfectly shows the challenge. Every single dot you see here is a potential brain configuration for the AI. Now, most of them are total junk. They just make the robot fall over or twitch. The good solutions are buried in there somewhere. Trying to find them is like searching for a few specific needles in a haystack the size of a galaxy. It's a non-starter.
So how in the world do you solve an impossible search problem? Well, you don't just search harder, you find a better map. And that is exactly what the researchers behind this paper figured out how to do.
This brings us to the core aha moment of this whole thing, called the manifold hypothesis. The idea is that all the good working solutions, they aren't just sprinkled randomly all over that giant space. They actually tend to clump together on a much simpler, hidden structure, kind of like a secret road system or a surface that's tucked away inside that massive, complex space. If you can just find that hidden structure, that manifold, you've basically found the treasure map.
Now, I know this diagram looks a little intimidating, but the concept is super clever. To find that map, they use a tool called an autoencoder. So first, you see on the left, the encoder part takes a working solution, a point in that giant, messy space, and it squishes it down to a single, simple point on a much smaller of latent map. Then, the decoder part tries to take that simple point and blow it back up into the original solution. By doing this over and over, the autoencoder gets really good at it, and in the process, it learns the actual shape of that hidden treasure map.
Okay, so once you have the map, you need a smart way to actually explore it, and that brings us to the full algorithm. And that algorithm is called Policy Manifold Search, or POMS for short. And the strategy is it's beautifully simple. Stop wandering around lost in that cosmic haystack. Instead, do all your searching directly on that simple, easy-to-navigate map that the autoencoder just found for you.
So how does it work? Well, it's basically this continuous loop. First, it grabs a few good solutions that it already knows about. Then, and this is the key part, it explores around those points by taking little steps on the new map in that latent space. Finally, it checks out these new potential solutions. If they do something new and interesting, they get added to the library, which makes the map even better for the next round.
But hang on, this brings up a really subtle but absolutely critical problem. That map is a compressed version of reality, right? So a tiny 1-inch step on your map might actually be a 10-mile jump in the real world. So how do you make sure that a small, careful step on your map doesn't turn into a huge, chaotic, random change for the actual robot?
And the answer is a very clever piece of math using something called the Jacobian. You can think of the Jacobian as a local guide. For any point on the map, it knows exactly how stretched or squished the terrain is right there. Without it, like you see on the left, a small step on the map could be a disaster in the real world. But with the Jacobian, POMS knows exactly how to adjust its step size on the map to get a small, predictable, and useful change in the robot's actual behavior. It's the secret sauce that makes the search controlled instead of chaotic.
So the theory is elegant, for sure.
But does it actually work any better than what we already have? Let's take a look at the results.
So, the researchers put PALMs head-to-head with several other top-tier algorithms on some pretty complex robot tasks. The way they measure success is by looking at discovered behaviors. Basically, what percentage of all the possible cool solutions did the algorithm find in a certain amount of time? The higher the line goes on the graph, the better it's doing.
And the results? Well, they're not subtle. They're crystal clear. In test after test, that blue line, which is PALMs, just shoots up faster and goes higher than everything else. Whether it's a simple walking task or a more complicated kicking one, PALMs just finds way more diverse solutions and it finds them faster. It is simply better at exploring the world of what's possible.
And just to really drive that point home about the Jacobian, check out this quote directly from the paper. They tried running PALMs without the Jacobian, and the performance just fell off a cliff. The search became, in their words, almost random. This proves that finding the map isn't enough. You have to know how to read it, too.
So, what's the big picture here? What does this all mean for the future of AI and robotics? This is where it gets really, really exciting. So let's just sum up the core idea here. Policy manifold search gives us a powerful new way to think about this problem. It shows us that good solutions are hiding on a secret map. It gives us a tool to find that map, and it teaches us how to explore it intelligently. The end result is that rich library of diverse solutions we were after from the very beginning.
And this image, for me, just perfectly captures what that looks like. This isn't just a data plot, it's a picture of what resilience looks like. Each one of those colored lines is a totally unique strategy that PALMs discovered for an air hockey robot to hit the puck. It's a visual catalog of hundreds of different plans. If one approach is blocked, no problem. It's got 1,000 others it can try.
And this brings us right back to where we started. Remember that robot with the damaged leg? This is how you solve that problem. By building these huge catalogs of behavior, we are taking a massive step toward creating AI that's genuinely adaptive, robots that can recover from getting hurt and react to a world that's constantly changing, a lot like animals do.
So it leaves us with this one last, really powerful question to think about. For so long, we've been obsessed with training AI to find the one best answer. But what if we can teach it to discover and navigate an entire landscape of good answers? What new kinds of problems could we solve then? What new frontiers of creativity and resilience could that possibly unlock?